Guys, welcome to the Data Science Nigerian online class in preparation for AI Bootcamp running, and we have 100 days crash course on machine learning and deep learning. And actually 100 days I think is quite enough time to going deeper into machine learning, and you can be a good data scientist in this time with the ability to understanding the theory of machine learning. So maybe you should ask, maybe you ask yourself, okay, why should I know about the theory of machine learning and deep learning while there are lots of packages in Python which I can work? The fact is that there are lots, and in fact there are tons of data scientists and machine learning engineers out there. If you want to actually getting a good job and stand yourself in front of others, you should have a better understanding in comparison with others. So for better understanding, you should know about the theories and algorithms, how the machine learning algorithms work actually. And so, and 100 days actually is enough, as I mentioned, for getting familiar with machine learning. And I'm Mehdi, you could call me Mehdi. In here I'm just scribbling, I think, but sorry, so this is not my actual handwriting, but on these boards I'm relatively new to these smart boards, so yeah. Okay, Mehdi Ayubzadeh. I'm doing my PhD in McMaster University, and yeah, that's it. And actually researching on deep learning things and image processing. So we are going to getting familiar with these things in the future. At first we are going to talk about machine learning. So the reference is this book actually. If you want to, you can download it. It is free. So it's pattern recognition and machine learning, and the author is Bishop. It is quite good book, and actually the main reference in the most universities and schools for the machine learning, and it is quite a good book, and we are going to learn from this book. So you could study this book after I teach some of the materials, or before that you could read the materials in advance to have a better understanding of the things that I teach you. So yeah, the first question, okay, let's start and go to the machine learning. Maybe before that it is better to make the outline more clear. So first we are going to learn about the machine learning things, the classification things, what is machine learning things, and probability, and all of the required stuff actually you need to know about machine learning. After that we are going to actually a little bit about computer vision, because probably most of you want to use the deep learning for image processing, so it is very good to have some knowledge about computer vision and image processing. And after that we are going to learn deep learning together, hopefully. And yeah, that's it. So let's start with the first one, which is machine learning. Okay. What is the first question is that, okay, what is machine learning? What is machine learning, which we show it typically by ML? The machine learning is actually means that finding some irregularities and laws in the data in order to make some actions. Let's give you an example. Suppose we have some images like this, and we want to recognize the digit inside the images. Just for the sake of simplicity, suppose that they are 28 by 28. Actually, this is a very famous data set. In the future, we are going to being familiar with this data set much more. This is called MNIST data set, but for now, just suppose that we have some images which have some digits in there, and we want to recognize that. So actually the 28 by 28 image means that we have a matrix of the, you know, each pixel has a real value things. So it could be 0, 0, 0, 255 or something like that, or whatever it is. We could vectorize this image and put all of these and stack all of these rows together and create a big vector. It is actually 28 by 28, means that it is 784. It has actually 784 elements. Okay, this is, suppose we call it x. Yeah, the x means that x, I don't know, x1. Okay, it's something like this. And we know that actually we are going to find a mapping from this x to a number, to an actual digit, which could be, which we could call it y, and it could be 0, 1, 2 till 9. So the actual things in machine learning, actually this is a specific task which we are going to talk about it later, but you can think of that as a mapping. So we have some x, and we want to find a function that we could apply on x and getting the digit. In this case, we want to put the image in here and get the y by just applying the f. And the machine learning tries to learn this f based on some data. In reality, we have some data in advance that have some labels. For example, a person maybe labeled them for us. We have 0, 2, 1, blah blah blah, and we know that this is 0, this is 2, this is 1, this is 4. This is actually data first, second, and third to n. We have n data. So based on this n data, we want to find this mapping. And so we can show this as x, actually x1, x2 to xn. We call this actually data set. And the digits in there, which are our targets, we could put them in a vector, and we could call it target vector. Okay, so the training means that from these available data with corresponding labels of them, we want to change the parameters of f, because probably f has some parameters in that, and we want to change the parameters to find this mapping between x and y. And after this training phase, we are given a new image, call it x hat, and we want to predict y by applying this f to x hat. So this is our purpose. Maybe you ask yourself, okay, how to represent the targets? The simplest thing is that put 0 to these things in here, but maybe it is not very good. We will talk about it in later. For the representation of labels, we have different ways, and actually you will see that, so don't worry about that. Okay, so this is training phase actually. Now in here we have some new images and we want to get in the labels. We call this phase as test phase, and the performance of the model in this phase is very important. We call this the generalization. The generalization means that, okay, after the training, how much your model is going to predict well on the test data, on the new images. Because maybe you train the classifier which predicts very good on the training data, but does not perform very well on the test data. This means that your model has very poor generalization. Okay, so, and this is very important actually. We will talk about it later in actually deeper things later. Okay, maybe we have another step called preprocessing. Preprocessing, yeah. In preprocessing, maybe in our example of digit recognition, maybe we scale all of the images, because maybe we have 32 by 64 or different scale images. We could scale all of them to the same size to have standardized data set. This reduced the variability of the training data and maybe make the training of the model easier. We call this preprocessing. We're actually changing the training data in such ways. Or sometimes instead of preprocessing, we call it feature extraction. And for feature extraction, actually, sometimes maybe you, instead of using the pixel values as the input, you use the width of this maybe and the height of this as your input. So instead of having 22 by 22 dimensions vector, you will have a 2 dimensions vector, because if you use the pixel values, you have 7, 5, 6 elements, means that you have 7, 5, 6 elements vector in this dimension, which is very high dimension. And but with this representation, you just have 2 dimensions for your x. Let's call it x prime. So you reduced your feature vector. We call it dimension reduction because we reduced the dimension of the data, and in here we lost some data, so we should very be careful in this step, and this is very important step in machine learning tasks. Okay, so in general, the machine learning tasks are 2 different categories. The first one is supervised, and the second one is unsupervised. Okay, in supervised means that in the data set that we have also the corresponding labels. In the digit recognition example, for the training phase, we had some images and the corresponding labels. We know that this image is 0, this image is 2, or something like that, because a person labeled those for us. This is actually a discrete example in which your output is discrete. The output could be 0, 1, 2 till 9. If the output is discrete, we call it classification, or sometimes maybe the output is continuous. In this case, we call it regression. For example, suppose you want to predict the price of the home. Oh, oops. What happened? Okay. Sorry for that. But, okay. We cannot. Price of the home or house based on the area and location. So the area and location will be our 2-dimensional x, and the price, which is a real valued output, is y, and this problem is a regression. The second category is unsupervised. In unsupervised, we actually want to know more about the data themselves. The training data does not have any corresponding label. An example would be clustering. Maybe we just have some data, suppose in 2-dimensional space, x1 and x2, we have some data like this. We don't know any label about them, but we just want to cluster these data. We don't know their labels, but probably these are in one cluster, these are in one, and these are in one. So we call this clustering. Okay, we don't have any labels for them, but we actually cluster them. Yeah, you can think of that in such kind of segmentation tasks in images. mostly. So this is clustering, and or maybe density estimation. Density estimation. In density estimation, actually we are going to find the distribution of data. The data, finding the distribution of data maybe could help us in producing more data. And when do we want to use it? Maybe I don't know, suppose you are going to creating a game, a video game, and you want to have different characters, I don't know, with different face, and you have some data which you have some faces in that, and based on these faces you want to create realistic faces but different from this training phase. In this case, you can find the distribution of your training data and just get new samples from the distribution. If you don't know much about the probability, don't worry, we will talk about the probability again if you don't know much about it or you forgot it. So don't worry about it. And sometimes maybe we want to project the data into 2 or 3 dimensional space to visualize them. It is actually very important one. Like for example, if you have some images, the dimension of these images is very high actually. It is, if it is 28 by 28, which is very small images, it is 756 dimensions, which is quite high. So in this case, maybe we want to have some sense about the images in 2-dimensional space. Maybe we could map the zeros, ones in here just to visualize how zeros, ones, 2 are positioned in the space. Okay? Okay, so this is the 2 category, general actually categorization of the machine learning tasks in general. Now we are ready to see an example from the supervised learning. It is quite beneficial to see an example. Our example will be about the polynomial fitting. We will talk about it. Okay, let's say you have some x which are real valued, and we want to find the mapping between x and y also is real valued. So we are going to solve a regression problem because y is real valued and a continuous thing. You could think we generate some synthetic data with this function and add some noise to it. The noise comes from the Gaussian distribution. You can think of that. Again, if you don't know much about this notation, don't worry, we will talk about it in the next session, I think. Okay, now maybe it is better to show it from the book. Okay, if you produce the data, you will have something like this. This is actually the sign of 2px, and these are the sample data. Okay, now the problem is that you want to feed a model, a polynomial model to this. So in other words, our f, or our machine learning model is a polynomial thing. Maybe it is better to show it as a function of x and the parameters w, which are the parameters. We could think that the degree of this polynomial is m, so we could show this in this way: 2m w. Yeah, okay. So this is our machine learning model, and based on the training data, our purpose is to use the training data, which we have some x and y, some sampled from this, and we want to actually estimate this function with this polynomial based on this data. So the parameters of this model is the weights in here. It is very important to note that this function is linear based on w's and non-linear based on x, because we have x power 2 and power m in general, but based on the w's all the power is 1, and so this is linear based on the w. And so it is very important. For this reason, actually, we called it linear models, and we study them later in a much deeper sense. So now, for finding these based on the training data, a very simple criteria is that we create a cost function, an error function, and then minimize it based on our parameters. So in other words, we have a fitting problem, so we could define an error which could be a mean squared error. If we have n data, we have something like this, minus, we call the corresponding label of x n's tn's. So this is the mean squared error for all of our data between the prediction of the model and the real value of the samples. Basically, it means that, again, from here, what is the distance? Yeah, we take these distances. This is actually the polynomial line, which is our machine learning model, and we take these errors and square them and sum over them. So this is actually this 1/2 is not very important. It's just one to for the convenience of mathematics things, so it is not very important. You could ignore it actually. So with minimizing this error based on e, you could derive a value for w's and derive the w's. For this, you could actually take the derivative from this and make it equal to 0, and then derive your estimation. Simply, you could derive that the W's, if you put all the W's in a vector, means that W0, W1 all in a vector, and call it capital W, the W is equal to this thing. It is actually a very famous thing, if you know that. It is called normal equations. Yeah, it is T, and the capital X means that all of your training data together, and the T is actually all of the target values. So this is the W, the weights. We are going to talk about this in deeper sense later, so if you don't know how to derive this now, don't worry about it. Just know that you could solve it easily and derive a unique value for W's, okay, to minimize this training error actually. So if you plot based on the different M's, okay, if your M is equal to 0, means that just remember what was the M. The M was the degree of this polynomial. So if the M is 0, means that we just only have one number in our model. We call it a bias maybe, or something like that. So we just have W null, and which is these. So our prediction when the degree of our polynomial model is 0 is this line, which is not very good. You can think of, you know, the real thing which we want to estimate is something like this, but we obtain something like this. If we increase the polynomial order of our machine learning model to a linear thing, we could derive something like this. You can think that in M is equal to 3, and you could derive something like this, and if you increase your M, you could derive the 0 training error. In this case, when M is equal to 9, means that you have a 9 order polynomial. In this case, your machine learning model is something like this, and as you could see in these points, the machine learning model is exactly like the sample data set. So this error is actually 0 for M is equal to 9 is 0, but the question is it a suitable thing? You could guess that very easily. The answer is no, because the generalization of this model is worse than this model. If you have a new data, new test data in here, suppose let's say we have a sample from here, the error will be this much. I don't know where is the climax of this function, but the error will be quite high. So the generalization of this model is not very good. As you could see that it is very it has very steep changes. So but you could see that M is equal to 3 is relatively good, although it does not have the 0 training error. In here you could see the difference between the machine learning model and the sample data. So the training error is not 0, but it is in general a better model for us in comparison with this model. It is very important. It is the difference between the machine learning and optimization. In optimization, you just derive the 0, you just minimize this thing, and okay, when it is 0, all the thing done, because you just want to minimize something. But in here the generalization error is is important, not the training error itself. So what should we do? Because we don't know how much M should be already or in advance. So we should somehow guess M or what? Okay, one way actually to, as you could see, if we reduce the M, we are reducing the model complexity. When we reduce the model complexity, we could not define lots of functions, lots of family function. And in very extreme case, when we have a bias, we just can have this line or this line, this line, this line, very limited family in comparison with linear models, which you could think of that we could, all of these things we could show in a linear models in comparison with just bias. The same things happens when we increase the M. So one way to create a balance between the complexity and the flexibility of the model is to regularize the model. In other words, in here we call this, in here what happened, the training error is very low and the test error is quite high. In this case we call it overfitting. Okay, and to solve overfitting we could done some different things. The first thing is that we could increase number of data. This is the simplest way, but we don't have always enough data to increase them. If you increase lots of data in here, these ninth order polynomial could not overshoot in here and it will be feed to the actual line. Let me show you this. If in here we increase the number of data, and as you could see, although the polynomial order is quite high, is 9th, but we have a very good estimation of sign. So one way is to increase the data, which we don't have access to it always. So the second way to solving the overfitting problem is to regularize the model. Regularize or regularization, which in this way we try to balance the model complexity and the flexibility of the models. This is actually a very broad category of the methods and approaches. So we just want to talk about an example about this to have a sense about what is the regularization. Let's say we change the cost function in this way. We have the mean squared error, and we add a new term which is the norm, which is the second norm of the weights. Okay, this thing is actually, you could think of in this way. Okay, so it's pretty straightforward. In here, as you could see, we are penalizing the large weights in the model. In here, when you have some overshoot, means that probably you have some very large weights. Let's see the, okay, as you could see, when you don't have the regularization term, means that the lambda is equal to 0. Let me show you again. If the lambda is 0, we just have the mean squared error, which is the very normal thing. Okay, if you have the 9th order polynomial and actually your machine learning model is something like this, let's see what is the coefficients of this polynomial. As you could see, we have some very large coefficients because of this fact that when it goes very up, means that you have very large coefficients, so you should have another very large negative coefficients in order to negate that positive things and return it back in here, and you know, this makes the situation worse and worse. So you have very large coefficients. So if we penalize these large coefficients in the cost function, probably we are going to do better, just probably. So we guess that. So we could do that actually. If you do this, in here you could again think, in here you could see that the m is equal to 9 again. When you have lambda is equal to ln of lambda is equal to 0, means that the lambda is minus infinity, you will just have a line, means that you are penalizing the you are penalizing your weights too much. So yeah, so you just have a very slight thing from 0, means your weights are very small things, because if they are going to be large, this, where was that? Okay, this cost function, this term actually dominates over this term and penalizes them so much. So they are, if you make the lambda so large, these terms actually dominates these terms, and you could ignore this term. So the doubles you use are going to be 0. This is not actually very good. So you should have a balance between this term and this term with setting lambda properly. You could have a balance between these two. Let me show you. In this case, if you have a more or proper lambda, in this case you will see that although your polynomial order is still 9, in these 3 examples, in this one, in this one, in all of these examples, the polynomial order or the machine learning model has 9th order polynomial thing, but the lambda is different. So you could see that for some lambdas we are going to have very nice and smooth plots, so which has very good generalization. So a very good question is that, okay, how should I find the m or lambda? A very good way to do this is, you could, if you have your training data, you could split it again into training data and validation data. So you could derive your model parameters or W with this training data, and then test your model on this validation data in order to tune the lambda and m. If you do that, you will end up with something like this. This is RMS error. The RMS error, it's actually not very difficult thing. It's just kind of the normalized E. The E means that that mean squared error is just divided by n, and because we want to make this error independent for different size of data sets, so we divided it by n. It's very simple. So if you plot that, this is the training error. As you could see, if you have very large lambdas, for very large lambdas, and you will have probably high test and training error. In this case, your W's will be quite small because you are penalizing them so much, so they are going to be small, and then your training and test error will be quite high. It happened in this case, so it is not very good. If you have very small lambdas, means that you actually don't penalize your weights of model at all. It means that you just have this term, which is the mean square term error. So, and we are ignoring it when you put the lambda is equal to 0. So you just have this term. In this case, you will have a perfect training error. Your error will be equal to 0, and you will fit all the data perfectly, just your training data. This is actually this case. You will have 0 error in training data, but the generalization will be very poor, which is this one. Actually, we could use the validation data for this. In some range of lambda, you could see that the error both for training and test will be probably good and proper, so you could set the lambdas based on this plot in this range. So you should use the validation data to tune the lambda with this manner and with this with this phase, so it is not very hard. We call it, as I mentioned, we just split the training data into 2 different sets. Sometimes you could see that it is 70%, maybe it is 30% for training and validation. And you should note that the test dataset is separated from this. Sometimes if you just have one whole data set and you want to split it into training, validation, and tests, you should actually, it is not a very it doesn't have a very strong rule, but as a rule of thumb, sometimes we split it into 7, 20, and 10% of the whole data. This is for tests, this is for validation, and this is for training. Later we will learn something like k-fold cross-validation in order to use all of this data for training, not just this, but now we will call this holdout. In holdout means that we just hold some of the data for validation, for tuning the hyperparameters of our data, our machine learning model. So yeah, I think for yeah, maybe it is enough for this session. I hope in this session you are now grasping some ideas about what is machine learning and what are we going to talk about. For the actually Friday maybe, or Saturday, or I think the Friday is question and answer session. As an exercise, you could do this in Python in order to do some practical exercises. You should generate some data based on this model, which epsilon is a random Gaussian distribution. It comes from Gaussian distribution, and then obtain the W's based on different m and plot them with matplotlib. So if you don't know about the solution of where was that, about the solution of this equation, it is very simple. I write it in here, so you could use it in order to calculate the weights and create your polynomial model. This is the general solution, in which y is your target vector, the capital X is your feature vectors. It is very important to know that how to use the X when you have when you want to use this model. In this case, m is equal to 2, and you should note that you should put these in X, so you will have something like this probably, 1x1 and x1 power 2. And because this is actually W null times 1, so yeah, you should put all of your data in this matrix, and then yeah, calculate this. So yeah, you should code that in Python. It is pretty straightforward. Ask question if you don't know about this exercise, or if it is any obstacle in front of you, just ask it. So yeah, that's it for the first session. I hope you enjoyed from the first session. So see you, I hope actually to see you in the next sessions. Bye.